All right, good morning, everyone. So today, I'm really excited because we're about to be done with complex analysis and we're about to start getting into some really, really neat physical modeling of interesting systems. Fluids, elastics, quantum mechanics, optics, heat transfer. We're going to be able to start solving really, really powerful problems now in PDEs and advanced ODEs using some of the tools that we've learned in complex analysis. So I've almost taught you everything I wanted to tell you about complex analysis, and I have 2 more lectures. And so during these 2 lectures, we basically have all of the tools to start solving really, really complicated, interesting integrals. And we also have the tools to start doing things like analytically computing inverse Laplace transforms and Fourier transforms, which are going to be really, really important for solving PDEs. Okay. I cooked up a code last night that I wanted to show you, because I think a lot of what we're talking about with complex functions can be a little bit kind of abstract. And it turns out you can actually plot these complex functions in MATLAB and visualize the surfaces to see what things look like. So it's actually not as complicated as I've been making it. Okay, so we all remember the mesh grid command, hopefully, from last quarter. So if I want 2 variables, x and y, and I want an entire domain, maybe a rectangular domain in x and y, from -10 to 10 in x and -10 to 10 in y, I can use this mesh grid command, and I get this big array of x and a big array of y, all the x values in that 2D array, all the y values. And what I'm going to do is I'm just going to compute the logarithm of x plus iy. Okay, so I have maybe a 20 by 20 patch in the complex plane, and I'm going to just take and compute the logarithm. The great thing about MATLAB is that it can absolutely deal with complex numbers. It can do e to the complex numbers, log of complex numbers, not a problem. And I'm going to plot the real, imaginary, and absolute values of this thing. Okay, any questions about this code? All right, let's plot this. Let me try that again. And I'm going to use some fancy commands like face color interp, edge color none, and face lighting fong, which is obviously the best way to light a face. Okay, so this is what our real and imaginary parts of our complex logarithm look like. So the top, we have this nice singularity that we talked about before. So this kind of goes down to -infinity at the origin. That's what we mean by a singularity. This looks like a black hole or a blue hole. And this is the imaginary part of my complex logarithm. But what's wrong with this picture?
Can't handle more than one value in the vertical direction, so just...
Exactly. It can't handle more than, it's not going to give me an infinite vector of imaginary parts. It's going to give me the principal value, the, 0, actually negative pi to pi is what MATLAB gives me. Interesting. So I'm only getting one branch of my complex logarithm. Okay, but you do clearly see that if I started doing an integral, around a circle containing 0, I would pick up 2 pi in the imaginary part of my log z. My real part, I would integrate to 0. Okay, and there's this weird thing that happens at the point z equals 0. You see this crazy cusp where it actually is kind of not just infinite discrete values, but it has a continuum of values from, all along this vertical axis. Okay, so the last thing I want to do is I thought to myself, how do I make that spiral staircase plot in MATLAB? Okay, and it's actually a lot easier than I thought it would be. Actually, I thought this might do it, but it didn't. So now what I'm going to do is I'm going to create another mesh grid, but I'm going to create this in polar coordinates. Okay, I'm going to have r and theta are a mesh grid, so my radius is going to go from 0.1 to 10. So that's kind of a circle of radius 10. And my theta is going to go from 0 in increments of 0.1 up to 20, which is like 3 periods. Right? That's about 2 pi's. Okay, I can create my x and y, and I can take and analytically expand my log as log of the radius plus I times theta, because we know that that's exactly true. And now when I plot this, I get my awesome multi-tiered stair kind of function here. So this is a visualization of 3 branches of our complex logarithm. The coloring is just by height. The coloring means nothing. And this is just the imaginary part of the complex logarithm. Okay? So you can really visualize these things. You can create plots. One that I really like is to plot, instead of the imaginary part of z, I like plotting the absolute value of z. Which looks really strange. So this is the absolute value of, log of z. If anyone has a 3D printer and would like to print me one of these for my desk, I would be totally cool with that. But it has these great kind of weird cuspy features. So you can see that it has the singularity, the black hole, but it also has this kind of multi-valued weird branch point at z equals 0, this multi-valued thing. So this is like an especially weird version, absolute value or magnitude of log of z. Sorry, absolute value of log of z. Okay, that's what I wanted to show you in MATLAB. Any questions before I shut it down? Okay, good. Okay, so today what I want to do is just very, very briefly summarize the things we've learned and then use these to start showing you how to solve really, really interesting and powerful integrals. So we've learned what types of functions are or are not analytic, and I've asked you this every lecture, and I'm pretty sure you all know what they are now. We know that if we integrate an analytic function over an analytic domain over a closed curve, then that integral equals 0. Okay, that's the Cauchy-Goursat theorem. We know that if we integrate a complex function and there's some singularities in the middle, as long as I have my contour integral in some analytic domain, I can continuously deform it any way I want within that domain as long as I don't break the curve. And the most important formula we learned is the Cauchy integral formula. This was just yesterday, which is, how do I want to say this? So the closed integral around a contour C of f of z dz divided by z minus a is equal to 2 pi I f of a. And there's some conditions. That's if f is analytic in C, and this point A is inside C. That's it. Okay? If I have an analytic function, somewhere inside my closed contour C, and I have this point A which is inside that contour, I add the singularity, and this is what my integral equals. This is going to allow us to solve tons of awesome integrals that we didn't think we would be able to solve. Okay? Now that you've had some time to think about it, are there any general questions about this Cauchy integral formula? Okay, there's one more useful fact I want to tell you, and then we're going to do some examples. So for the next 2 days, we're just going to do examples, okay? Because I want you to actually have some experience doing these crazy integrals, because I'm going to ask you some of them on exams. So a final useful formula. And this formula is called the ML bound. ML bound. So the idea is, if I have some function, if my function f is bounded, if the absolute value of f is bounded by m, meaning that the radius of f of z is less than m on my contour, and if the length of my contour so the integral over my contour of ds is equal to L. So I'm defining m as the bound of my function on a contour, the biggest value that it reaches on the contour, and L is just the length of the contour. Then the absolute value of the contour integral of f of z dz is less than or equal to m times L. This actually makes perfect sense. I'll draw a picture. This is like extremely intuitive why this is true. If you could explain what a complex integral was to a 5-year-old, they would probably believe this after you draw the picture. So the basic idea is that I have some contour C, and it has length L. Okay, so what I'm going to do is this contour can have singularities in it. Okay, this integral might not equal 0. It might equal some crazy stuff. There might be a ton of singularities inside of here. Okay, we're not getting the exact answer of what this integral equals. We're just getting a bound on how big the integral could possibly be. And so the idea is, this is like a worst case scenario bound on what the integral of f could possibly be. Okay, this is a worst case scenario. So f has a bunch of values, right? There's some f value here and here and here and here. My function has values all along the circle. And one of those values is going to be larger than all of the other ones, right? Unless there's a singularity, in which case it would be like infinite. But one of these function values is going to be larger in magnitude than all of the other ones. Okay? That's m. That's the largest function value, the absolute value of f. Now imagine in the worst case scenario, the entire function along the entire contour was equal to that very large value m. Okay, so my entire function is just, let's see if I can draw this. So in the complex plane, I have my contour, and I have some function on this circle, which is, it's going around the circle, looks like a ring or like a crown or something. This is the largest value, m. And what we're assuming is, how big would this integral be if the entire function on this entire integral was equal to m? Okay? And that's exactly equal to m times L. If my entire function was a constant equal to m, and I integrated m over my contour, I would get m times L. So that's the biggest this integral could possibly be, is if f was equal to its largest value on the entire contour. For any other possible f, these values might be smaller than m, or some of them might be positive and others might be negative, and they'll cancel. And so this integral is always going to be less than m times L. Less than or equal. It could be equal if I have a really boring constant function equal to m. Okay. Questions about this? I see some unease.
Why are we interested in knowing this?
Why are we interested in knowing this? That's a great question. So, yeah, really, really good question. So what we're going to do, So this is a good segue into the next portion. Let's say that I have some really nasty integral that I want to perform. Let's say that I have my complex plane, and I have some function that has some singularities. Okay? Some function f of z has these singularities. And let's say that my boss tells me I need this integral here. Okay? I need the integral from minus infinity to infinity of f of x dx. It's a really nasty integral. I didn't tell you what f of x is, but it's nasty. Okay? So if your boss wants this, often what you can do is you can create a big circle enclosing those two poles. So this is a circle of radius r. Okay? So this is C1, this is CR, and the whole contour is C. So the integral around this entire contour of f of z dz is equal to the thing I want. I have to take the limit as r goes to infinity. Okay, it's the thing I want plus this big, huge integral around this very large radius contour CR. Okay, let's take a step back. I'm trying to solve this real valued integral from negative infinity to infinity. Okay, I need to do that. Sometimes what I can do is I can take and create a closed contour C by making this big radius R loop and connecting, and taking the limit as that radius grows to infinity. And as I do that, I can break this contour up into the part I want, which is a real valued integral along the x-axis, plus this integral around this really big circle R. Okay? Now, I just took your question of why we're doing this, and I pushed it to another question. Why does my boss want this? But just take my word for now that we actually do want to solve integrals occasionally, and sometimes they're nasty. And so we can use the ML bound to show that this term goes to 0. Now, that's not always true. But for lots of functions, as I increase the radius, the function gets smaller faster than the radius gets larger. And so m times L will limit to 0. So this is a very, very powerful theorem. I can make this term 0 sometimes, and so I get that this real valued integral that I want is equal to a complex valued integral with a few simple poles inside. And just last lecture, we realized we found out how to solve this integral using the Cauchy integral formula. Okay, so I can solve my real valued nasty integrals using the Cauchy integral formula. That's my next example. Okay, so we'll actually do this for f of x that I name. Okay, any more questions about the ML bound before we go on? Maybe I'll just do a really simple real valued example. Let's say that I have the integral of x squared from 0 to 1. Integral from 0 to 1 of x squared dx is equal to x cubed over 3 evaluated at 1 and 0 is just 1/3. Right? Simple. The area under this curve is 1/3. Now let's try the ML bound. What is the length of this curve in x that I'm integrating over? Just 1, right? If I integrated L equals integral from 0 to 1 of dx, which is just 1, my length of the curve is 1. What's the maximum value of x squared on that interval? 1. So m is equal to 1. And this integral, of course, is less than or equal to 1 times 1, m times L. That makes sense, right? Like, The worst case bound for this integral is if the whole function was equal to its biggest value on the whole domain, in which case the area would be equal to m times L, which is 1. This is just exactly what we're doing here in the complex plane. We've just done it using a fancy contour integral and a complex valued function. Same deal. Okay. So let me just color code this. M times L equals 1, and it's this green area here. Okay. All right, think about this. It's not the most, we're not going to use ML a ton, but you should feel comfortable with using it after we do a couple of examples. Okay. Okay. I'm going to do a simple example of the Cauchy integral formula before we try to tackle this really hard problem. Okay? So the reason we might want to solve some of these nasty integrals are, for example, to do inverse Laplace transforms, Fourier transforms. Every once in a while, there is a real integral that you really do want to solve, and it's nice to know how to solve it. Okay. So this is a simple example to get us started. And this is a simple example of the Cauchy integral formula. Okay. So let's say that my function f of z is equal to 1 over z squared minus 3z plus 2. Okay, this is my function. And I'm going to be able to factor this, so it's 1 over z minus 1 times z minus 2. So how many poles does this function have, and where are they at? 2 poles at 1 and 2. Okay, so in my complex plane, I have 2 poles at 1 and at 2. And we're going to quickly solve a bunch of rapid-fire contour integrals of this function over different contours. So first we're going to solve it over C1, over C2, over C3, and over C4. Okay, this is just a review of stuff we've already learned from the last lecture. Okay, so let's make a couple of important remarks. So first, note that I'm going to create a new function called g of z. So g of z equals 1 over z minus 2. G1, let's call this G2, is analytic near z equals 1. And our other function G1, which is just 1 over z1, z minus 1, is analytic near z equals 2. So I'm decomposing my function into, G1 times G2. And G1 is analytic near my second pole, and my second function is analytic near my first pole. Okay, which means I can apply Cauchy integral formula. So let's try integral around C1 of f of z. F of z dz. Okay, that's just equal to G2 divided by z minus 1 dz. Let me write it out long ways. This is the contour integral around C1 of 1 over z minus 2 times dz over z minus 1. Remember our Cauchy integral formula. We have this integral of f of z over z minus a dz equals 2 pi I f at a. Okay, so we're just doing this little contour integral here over one pole. This is my function, right? This is the thing I'm integrating. This is f of z. This part is analytic at my pole, right? So this is equal to 2 pi I times this evaluated at z equals 1 times, g2 evaluated at this thing here, my function, my analytic function evaluated at my pole, here is just 1 over z minus 2 evaluated at z equals 1, evaluated at the pole. Is this making sense? Or is this, how many is this making sense? How many would like me to say this one more time more clearly and slowly? Okay, a few of you. So let me just try this one more time. Okay. I'm taking this contour integral around a single pole of this function right here. This is the function I'm integrating around that pole. Okay? Now, this function, we can cast it into the Cauchy integral formula form if we want by saying that this is my analytic function f of z. This is analytic near z equals 1. And this is my 1 over z minus a. Okay? So this part is analytic around this pole. And this other part, this 1 over z minus a equals 1. And so the solution to this integral using Cauchy integral formula is 2 pi I times this function f evaluated at this pole a, which is 1 over 1 minus 2. So we get 2 pi I times 1 over 1 minus 2 is just minus 2 pi I. Okay, if this is still confusing, I'm going to post my notes online. You can kind of go over this again. Just try to think about how you can look at this contour integral in terms of the Cauchy integral formula, and it should make sense. Okay, so that's my integral of contour 1. It's equal to minus 2 pi I. Simple. Similarly, if I take my contour integral around contour 2, dz, it's the same thing, except now it's integral of C2. My analytic part now is 1 over z minus 1. Like, this is the part of the function that's analytic at my pole z equals 2 times dz over z minus 2. And so this equals 2 pi I times my analytic part evaluated at my pole. So 1 over z minus 1 evaluated at z equals 2. That's just f of a. And that equals 2 pi I, like positive 2 pi I. It's a little unfortunate that I chose the same function f here and here. This is just a dummy function that's analytic, not the same as this f. Okay, so what's the contour integral around C3 equal? Okay, how many of you think it is positive? Negative? 0? Okay. Why would it be equal to 0?
You can slice those contours up into 2, and then you have, you're going to take that one plus that one, and then minus what's in the middle of each of them. And you already know what those are.
That's basically the right idea. So if I have these two poles, and I have some big contour integral C3, then I can shrink that contour integral down to something that's basically a full loop around here, a full loop around here, and then these two segments that cut cancel each other out. So I basically have, integral of C1 plus integral of C2 is equal to integral of C3. And because one's plus and one's minus, they cancel out. It's just a coincidence for this problem that they cancel out to 0. Okay, so being familiar with how you can do this kind of mapping and surgery of these contour integrals is super, super important. Knowing that you can take your contour integrals and deform them as long as you're deforming them inside of an analytic region, that's probably the most, that's actually the most useful trick in solving these integrals, is being able to deform your contour to somewhere that your integral becomes simpler. And here, this is a lot simpler. Right? My plus and minus parts cancel, and I just get C1 plus C2. And what's the integral of C4? 0, right? Because the function is analytic in this region, even though it's got singularities over here. It's smooth over here. Okay, not as simple of a problem as I thought. Okay, so now we're going to get back to So now we're going to get back to this idea here, which motivated this ML bound. Okay, so we're going to take some function f of x that we want to integrate from minus infinity to infinity. And the way we're going to do that is we're going to first integrate this big closed contour, which we can do using Cauchy integral formula. And we're going to show that the radial part is equal to 0. So my Cauchy integral formula is going to equal my real part of this integral. Okay, I'm just going to go through this from scratch on a concrete example. And the only way to get better at this is to practice. So when I was studying for qualifying exams, we would get together in groups and do dozens of these integrals. We would just take a book and take all of the nasty integrals you're supposed to be able to solve with Cauchy integral formula and try them out. And you get really good at applying the techniques and simplifying the problems when you actually do some of them. And I can show you what the major tools are, but I can't get you good at using them until you actually start using them. Okay? Okay, so the problem we're going to solve, this example is slightly more difficult. So we're going to integrate a function from minus infinity to infinity, and that function is dx over x to the fourth plus a to the fourth. Okay? Does anybody know of a way to integrate this using calculus? Probably possible, but I forgot. Okay. And it's also interesting to note that this is equal to 2 times the integral from 0 to infinity of the same thing, because this is an even function. So you could also solve integrals from 0 to plus infinity just because it's symmetric for positive and negative x. Okay, so we're going to do this trick we talked about by creating a complex contour integral in the complex plane. So we're going to turn into a contour integral problem. Contour integral. And it looks almost exactly like what I just showed you. I'm just going to go through the steps really carefully and really slowly. So I'm going to take this function, this contour C1 plus CR, C1 plus CR, and I'm going to call that C. That's my contour. It's a closed contour. And when I take the limit as r goes to infinity of the integral of C1, of dx over x to the fourth plus a to the fourth. That clearly equals this thing that I'm trying to solve. Should probably put, this is minus r to r, and this is radius r. Okay? So I have this big radius r half circle that I'm integrating around, and the flat part of it, if I took the limit as r goes to infinity, would be the thing I actually want. Okay? So what I'm going to do is I'm going to turn this into a function of a complex variable z, which is fine. If I took that function and I integrated it on the real part, it would still be real valued. So I'm going to say I want the contour integral around c of dz over z to the fourth plus a to the fourth. Right? I just took this function, and every place I saw an x, I just put a z in. And if I integrate this on the real axis, these are all real again. Okay? This equals, I'm going to take the limit as r goes to infinity. This equals the thing I want, I, plus the limit as r goes to infinity of this radial contour integral of dz over z to the fourth plus a to the fourth. This is a common trick. I'm making stuff up right now. I basically have this integral I want, and so what I'm going to do is I'm going to close the loop. I claim that I can solve this part, so we can solve this using the Cauchy integral formula. Okay, I'll do that in a minute. And I'm going to set this, I'm going to show that this is equal to 0 by ML bounds. Okay, which would you like to see first? Would you like me to solve this nasty contour integral using Cauchy integral formula, or show that this big radial part is equal to 0? The ML bound part first? Okay, good. This is just accounting. We're just doing accounting. These things have to add up. Okay, and if this one's equal to 0, then I equals this. Okay, so how do we prove that this is equal to 0 by ML bounds? Okay, so what's the length of this big CR? Pi r. Okay? L equals pi r. Right? Length of contour. Not the counter, the contour. And now what I need to figure out is what is an upper bound m on my function on this entire contour. But what does this look like, my function? What is my function going to look like for big R? It's going to look a lot like 1 over r to the fourth. Right? Z to the fourth has a real part of r to the fourth. Not a real part, an absolute value, a magnitude of r to the fourth. So this thing m equals the maximum value of all of the z's on my contour of 1 over z to the fourth plus a to the fourth. And this is always smaller than or equal to 1 over r to the fourth. Like if I take 1 divided by r to the fourth plus 5, it's always less than 1 over r to the fourth. Basically what we're doing, but in the complex plane. So this function is always less than or equal to 1 over r to the fourth. And so if r gets really, really big, my function gets absolutely minuscule. And my function gets smaller faster than my curve gets longer. Okay? So the size of the big radius part of my contour integral is less than or equal to pi r over r to the fourth. So the contribution from this integral is less than pi over r cubed. And what am I doing to r? I'm taking r to infinity. So this term goes to 0. It's just a simple way of saying that the function value on this curve is so small that as I make that curve, infinite in size, even though the length of that curve is also infinite, my function gets infinitesimally smaller faster. And so it integrates up to 0 as r goes to infinity. This is why we use the ML bound, because we've just made this part here equal to 0. Okay? This is step 1. Okay, step 1. Step 2 is actually finding what I equals now. Now we know that I equals this contour integral. And I claim that we actually have the tools to do that now. Oop, just lost my papers. All right. All right, these problems are nasty. I wouldn't recommend, stressing too much about all of the little details. What I really want you to know is the big picture of how to solve these things, and I want you to have the experience to solve them if you have to. So just get good enough that you know the basic ideas. Okay, so now we're trying to solve the left function using Cauchy integral formula. Okay, so step 2, we need to actually compute this contour integral of dz divided by z to the fourth plus a to the fourth. Now, how can I solve this using the Cauchy integral formula? Is my function analytic on and inside this red contour? Or maybe ask another way, does this function have any singularities? Okay, some of you think yes, it has singularities. Some of you think no, it does not have singularities. Okay, it does in fact have singularities because there are roots of this equation. Okay, so my function, f of z equals 1 over z to the fourth plus a to the fourth has 4 singularities. Okay, it has singularities at z to the fourth equals minus a to the fourth. And we can take the fourth root of minus a to the fourth. So z equals a times the fourth root of negative 1. And we know that we can compute the fourth root of negative 1. We have a formula to do that now. Okay, so these singularities have radius a, and they're in the directions of the 4 roots of negative 1. So I'm just going to draw those. There's one here, 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 and here. We call this A1, A2, A3, A4. Okay? And if I really wanted to write these out, which I don't particularly, but I have to, they are plus or minus a plus or minus ia divided by square root of 2. These are the singularities of my function. My function is singular and blows up to infinity at these 4 points in z. Okay, so let me ask you again. Does this big red contour integral of my function equal 0? Probably not, because I've got singularities inside. I can't just offhand say that it equals 0 by Cauchy-Goursat, because it's not analytic inside C. Okay? So now what are my techniques for actually finding what this contour integral equals? Sorry?
That as a group of functions around your singularity.
Yeah, exactly. I can say that f of z equals, this is getting just nastier and nastier. I have z minus a1 times z minus a2 times z minus a3 times z minus a4. That's f. Okay? Now, if I zoom in, remember, we can always kind of rewrite this contour as this funny thing here. Okay, so I'm basically just trying to sum up the contour integral around this pole and the contour integral around this pole. That we can definitely do. So let's start with, this contour integral around A1 and this contour integral around A2. So my contour integral around A1. What part of this function is analytic near A1? Everything except for that. This part of the function is analytic at A1. Okay, so by Cauchy integral formula, I'm going to write this down. I'm going to say this is equal to, dz over z minus a2 times z minus a3 times z minus a4 times 1 over z minus a1. So this is the analytic part near a1. And this is my singularity. Okay, so what does Cauchy integral formula tell me that this integral equals? Good. 2 pi I times this analytic part where I plug in A1 for all of the z's. It's actually not terrible. Like, I'm not thrilled about what comes next, but this part's not bad. So this is 1 over a1 minus a2 times a1 minus a3 times a1 minus a4. Okay, that's the integral around that first green circle. Okay, walk me through the second green circle. It's basically the same. Okay, I want to hear from you all. How do I do the second green circle? Integral of c around a2. Okay, dz. And what do I want on this left side? Right, I want the analytic part, which is z minus a1. It's everything but the pole. Z minus a1 times z minus a3 times z minus a4 times my singularity, 1 over z minus a1. And again, exact same thing. It's 2 pi I times my analytic part evaluated at my pole. Cauchy was a genius. This is so much easier. 2 pi I times, now this is a2 minus a1, a2 minus a3, a2 minus a4, all under 1. Okay. We can plug in these numbers. A1, A2, A3, and A4. We actually know them. So I can plug these all in. It sounds horrible. I'm not going to do it. I'll just tell you what it is. I did it this morning. You get, so the integral of C1 plus the integral of CA2 equals pi over root 2a cubed. And this is equal to this big contour integral, which is equal to I, my real valued integral from negative infinity to infinity. This is I. You can actually code this up in MATLAB, make a bunch of little dx's, and integrate out sufficiently far, and I'm assuming it'll converge to something a lot like this. So test that out. That's something you can do like right when you go home. First thing you do. It'll be awesome. Okay, that's everything I want to tell you today. Okay, next lecture we'll do Laplace transforms.